Hello students, in this video we'll compute the sum of the reciprocal of the natural numbers using a double integral. Let's consider a sequence an, which is the integral from 0 to 1, the integral from 0 to 1 of x to the 2n, y to the 2n, dx, dy. We can rectangularly separate this, and the integral of x to the 2n from 0 to 1 is x to the 2n plus 1 over 2n plus 1. And so we see that this sequence is actually equal to 1 over 2n plus 1 quantity squared. Then the next observation to make is that if I sum this up, so therefore, this implies that the sum, n goes from 0 to infinity, of an is the sum, n goes from 0 to infinity of these double integrals, integral 0 to 1, integral 0 to 1, x to the 2n, y to the 2n, dx, dy. Okay. Now what I'm going to do is I'm going to observe that if I put this summation inside the integral, what I get is the following. So our summation, n goes from 0 to infinity of an, is equal to the integral from 0 to 1, the integral from 0 to 1 of the summation, n goes from 0 to infinity of x to the 2n, y to the 2n, dx, dy. And now this is a geometric progression, so this becomes the integral from 0 to 1, the integral from 0 to 1 of 1 over 1 minus x squared, y squared, dx, dy. Great. Now, here comes the fun part. We're going to change the coordinates in the following way. This is a beautiful trick. We're going to let x be the sine of u, the secant of v, and y to be the sine of v, the secant of u. So if I was going to change my coordinates, if I was going to change the variables, I need to do three things. I need to figure out how the limits of integration are going to change in the UV space. So in other words, if x and y reside in the unit square, where do u and v reside in the UV plane? How will my function change and how will my differential change? Let's first examine how the differential will change. So dx dy is what? Is the absolute value of the determinant of partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v, du dv. And so let's check out what this determinant is. What is this Jacobian over here? So we call this thing, this of course is our Jacobian j. So what is j? So j is going to be determinant. And what's partial x, partial u? That's cosine u, then secant v. And then what's the v derivative of x? It's going to be sine u, secant v, tangent v. Same thing down over here. I'm going to have a what? I'm going to have a derivative of y with respect to u is going to be a sine v, and then a what? And then a secant u, tangent u. And then the derivative with respect to v is going to be a cosine v, and then secant of u. That's our Jacobian. And now observe what happens on the main diagonal. On the main diagonal over here, we have a cosine u times a secant u, that's 1, and a secant v cosine u, that's 1. So the main diagonal gives me a 1. And what will the off diagonal give me? Well, it's going to be a total factor of what? Let's see, I have a sine u and a secant u. Sine u and secant u is the same thing as tangent u, and then another tangent u. So that's going to be a sine squared u over cosine squared u. So I'm going to have a sine squared u over cosine squared u. And then we have a what? The same thing, a sine squared v over cosine squared v. So what does that say? So I have a total of what? So we're going to have, well, let's think about this for a second. So what is x? X is really sine u over cosine v. So since I have sine squared u over cosine squared u and sine squared v over cosine squared v, what I really have over here is this is just over here, this and this is really going to be x squared, and this is going to be y squared. So our Jacobian, in this case, is just 1 minus x squared, y squared. So we see that I don't even need to put u, v variables in over here, because when I replace x's and y's with u's and v's over here, and I replace my du dv's with my x's and y's, my Jacobian, they will cancel out. So the 1 over 1 minus x squared, y squared will cancel out with the Jacobian term. And so when I change the variables, what will happen? Our double integral, integral from 0 to 1, integral from 0 to 1, of 1 over 1 minus x squared, y squared, dx dy will turn into the double integral over a region E of just du dv. So then we're going to have just the area of what? The area of E. So I just need to find where the sets, where the unit cube, where the unit square is going to go under this coordinate transformation. So let's think about that carefully. So let's note the following. So we can note that my unit square over here, so if x goes x between 0 and 1, y between 0 and 1, that's my region over here. And now what will happen in the E region? Well, if x is equal to 0, that says that u is equal to 0, and if y is equal to 0, that says that v is equal to 0. So in other words, we're in the what? We're in the first quadrant over here, so we're going to have u and v. This implies that u and v are greater than 0. And we can restrict ourselves to a square of length 2 pi because everything is periodic, so this will repeat, all these things will repeat themselves. And so the next thing to observe is that if x is less than 1, what does that say? That says that the sine of u times the secant of v is less than 1. So of course, multiplying by cosine will say that the sine of u is less than the what? The cosine of v. But the critical observation here is that the cosine of v by the cofunction identity is just what? It's just the sine of pi over 2 minus v over here, right? So now what I have, at least in the range, if I restrict myself to the region where I have u and v less than pi over 2, for example, to make sure that everything is in the right configuration, that would say that what? By the monotonicity of the sine function, that would say that u is less than pi over 2 minus v. So that says that u plus v is less than pi over 2. So our region is basically just a triangle. So our region in the UV space, our E space, so E, here's u, here's v. Of course, by periodicity, I can shift this anywhere else I want. All I need to do is find one version of this area, is this triangle over here. So that's pi over 2, that's pi over 2. This is u plus v is pi over 2. And we are inside this region over here. So the area of this region E is what? The area of this region E is just 1/2 pi over 2 times pi over 2. So this is going to be a pi squared over 8. So this double integral, so in other words, our sum of our series is pi squared over 8. Now the cool thing to observe is this. So we've just proven that the sum, n goes from 0 to infinity, of 1 over 2n plus 1 quantity squared is pi squared over 8. Now that's the sum of what? That's the sum of the reciprocal of the square of the odd numbers. Now if I want to do the sum of the reciprocal of the square of all of the positive integers, I'm going to make the following observation. If I did pi squared over 8, that are the what? Those are the odds. And then I add in the what? And then I add in the evens. Those are the evens. 2n will give us all the evens squared. That's the total sum. N goes from 1 to infinity of 1 over n squared. But the key observation to make over here is that this sum over here is really what? Is really 1/4 of the sum n goes from 1 to infinity of 1 over n squared by pulling out that factor of 2. So in other words, the sum we're after, so I have one full copy over here, a quarter of it over here. So that says that pi squared over 8 is 3/4 of what? So that tells us that pi squared over 8 is really 3/4 of the sum n goes from 1 to infinity of 1 over n squared. And then if I multiply both sides by 3/4, I can conclude the following. I can conclude that the sum n goes from 1 to infinity of 1 over n squared is what? Well, if I multiply by a 4, I'm going to get a pi squared over 2, and I divide by 3, I'm going to get pi squared over 6. So I get pi squared over 6, and we've just found the sum of the reciprocals of the squares of the natural numbers. And it turns out that this is an example of a one particular value of the Riemann-Zeta function, which is a very interesting topic and a very interesting problem in mathematics. Nonetheless, we found a really cool result by changing the limits of integration on a double integral. Thank you very much.